Hello everybody, welcome to the Veriest workshop where we will present you functional verification methodology for verification of functional safety feature of an automotive AI processor. My name is Mihajlo Katona and I will be your host today. I am from Veriest Solutions and we are an async engineering services company founded in 2007 in Israel. Today we have 4 additional sites in Europe and an engineering pool of more than 120 engineers. Our customers are many Tier 1 international semiconductor companies, startups, IP and EDA vendors. We are mostly engaged in a functional verification project, but we also have a representative design team and a formal verification experts. The methodology I will present to you today is developed with our fruitful and long-term collaboration with CEVA, a leading sensor of wireless connectivity and smart sensing technologies. The methodology baseline was defined while we were working on the AI processor architecture for imagining and computer vision. These principles are later confirmed in a SensePro project with functional safety features embedded inside a high-performance sensor hub DSP. This highly parallel processing DSP engine is tailored for different computer vision and deep neural network inferencing, simultaneous localization and mapping algorithms, rather processing and much more with highly modular and scalable architecture with different hardware configurations. I would like to thank to Mr. Noah Messer, Director of the VLSI Verification and Infrastructure at CEVA, for his support in all projects we have executed together, guidance in the methodology development, and valuable comments and suggestions during preparation of the slides for this presentation. So, what is functional safety? In one simple sentence, it is related to a safe machinery without causing any risk to human life. Functional safety covers an active system that has safety mechanisms in place. These mechanisms are activities or technical solutions to detect, avoid, and control failures or to mitigate their harmful effects. The safety mechanism is either able to switch or maintain the item in a safe state or able to alert the user to take control of the effects of the failure before human life is endangered. And please notice that if at any time this mechanism fails to perform the intended function, there could be damages putting human life on risk. We all know that the ISO 26262 is an international standard for functional safety of electronic systems that are installed in serial production road vehicles. This standard recognizes 2 types of failures. The first one is systematic failures. Those failures are induced in a deterministic way during development, manufacturing, or maintenance of the system. They are process-related issues and are having source in pre-production activities such as specification difficulties or manufacturing defects. The ISO 26262 is targeting to prevent and avoid those kind of failures. The second group of random failures. These kind of failures are the mainly target for the functional verification methodology we are presenting to you today. Random failures are related to any kind of random defects in process or usage conditions such as radiation or silicon wear out. Random failures are separated into 2 groups, permanent faults and transient faults. ISO 26262 targets to control random failures. The verification problem we are targeting here is that state-of-the-art functional verification methodology is not directly supporting verification of random failures within ISO 26262 requirements for functional safety. We believe that the verification methodology is required to distinguish functional safety verification from classical functional verification flow. For this, we need new tools and verification approaches and stricter and well-documented verification procedures. And our special focus are transient faults that can randomly upset the state of a system we are verifying. In a semiconductor world, functional safety is all about data storage and data movement through the system. Electrical or magnetic interference inside hardware system can cause single bit to spontaneously flip to opposite state. And this is a typical case for random failure, which we desperately need to analyze and see its effects on the functional behavior of the system we are verifying. For example, some statistic data that can be found are showing that error ranges from 10 to -10 to 10 to -17 errors per bit in 1 hour. Roughly, for 1 gigabyte of data, this is translated to a range from 1 bit error per hour to 1 bit error per century, Obviously, 1-bit error per century is not concerning us, but the other side of the spectrum is requiring our special attention. We can all agree that the error detection is of utmost importance in digital systems, and there are already well-defined and proven methods which can help us to control harmful effects of the random failures. Those methods are defined mid of the last century by those two gentlemen. Richard Hamming invented coding mechanisms, which is heavily used in computer memory systems, and Wesley Peterson invented cyclic redundancy check mechanism, which is applied in many communication protocols such as Ethernet, wireless and mobile communication standards, USB, and many, many more. Let us briefly see how those mechanisms work. Hamming coding and decoding is based on defining parity bits, which are kept together with primary data. With those parity bits, we can detect and fix 1-bit errors, which is a perfect mechanism for a single-bit random upset events caused by transient faults in a system. If we look at a simple academic example of data protection for one data nibble, which are 4 data bits, we need 3 additional parity bits, which are defined by combination of 3 primary data bits. At the receiver side, we are then getting 7-bit word, where we are doing XOR operation to get position of the errored bit. We do this by calculation of the syndrome, and this syndrome is defining a decision table. This table is then showing the status of the received word. Our target is to have syndrome equal to 0, which is meaning that everything is okay and there were no 1-bit errors at the receiver side. If syndrome is pointing to a bit position where parity bits are located, we see that there was a single bit upset event, but the primary data is not affected. So we can freely extract the 4 data bits and use them as they are further in the system. But if syndrome is pointing to a data bit position, this means that there was a transient failure on our primary data. And since we have a reliable information where this transient failure has happened, we can flip that bit back to its original value, and we have correct data. This method can be further improved by adding one additional parity bit that is covering complete 7-bit word. With this parity bit, we can not only identify and correct 1-bit errors, but we can also identify when 2-bit errors have happened. We see this if parity bit is 0 and syndrome is larger from 0. This approach can be easily scaled to more data bits. For example, with 64 bits, we can have single error correction and double error detection scheme for 57 data bits, which is more efficient from the data rate perspective compared to the shown 7.4 Hamming scheme. But in this case, the error correction rate is much less and is down to 1.4% compared to 8.33% for 7.4 scheme. So we need to carefully see our safety targets and choose how we will apply Hamming coding scheme. As the cyclic redundancy check is concerned, here we are encoding a data message by adding fixed length check value for the purpose of the error detection. If this check value is not confirmed at the receiver side, then the communication protocol is responsible for requesting data to be resent by the transmitter. This check value is called the CRC code and is defined with generator polynomial. This polynomial defines the length of the check value. For example, the Bluetooth baseband packet is protected with this 16-bit CRC code, and the Bluetooth baseband specification is giving guidelines to implement it with 16-bit linear feedback shift register, like shown in this figure. Summarize: error correction schemes are based on quite complex and sophisticated mathematical background, but the implementation is straightforward and based on XOR gates and shift registers. We need to be aware that this additional circuitry is having an influence on signal propagation through the critical data paths in design and is putting additional stress on time constraints. Also, area constraint must be considered when safety targets are defined. Let us now move to the functional verification and functional safety verification challenge. We are always starting from a design specification. Design team is doing their interpretation and defines microarchitecture for the safety features we are analyzing. On the other side, the verification team is doing independent analysis and is building the functional verification environment. The goal of the verification is to build a test bench and test plan for functional verification of the safety features in our design under verification. By the functional verification methodology, a black box verification approach is required to verify system only through the available interfaces without any knowledge of the actual implementation of design. Our reference standard, the ISO 26262, is defining the B model for verification. It is also starting with system definition or specification. Then we have a list of required actions before the implementation starts. This includes the hazard and risk assessment, safety goal requirements definition, definition of functional and technical safety concept, also known as safety microarchitecture definition, and then we can implement safety features. On the other side, we have verification and validation actions, which are paired with left side definitions. Those are safety executed pre-silicon, safety validation executed post-silicon, safety case audit assessment executed at the application level, and finally safety management during production. And all those verification activities are defining the safety V model as per ISO 26262 standard. If we take our design example, which is AI processor, we can see typical data flow processing architecture, getting input data from some data buffer. This data is then distributed to the processing elements through the specified data distribution network. In AI processor, data processing is based on multiply and accumulate architecture. This processing block is usually parallelized and can have some additional internal memory buffers that are supporting the required data transformation flow. There can be also some post-processing mechanisms further in the data flow pipeline, before the results are sent to the output memory buffer. And as usual, there are some configuration and status registers where user can navigate the data processing flow according to their needs and monitor relevant status information. We see that there are different memory blocks in this data processing pipeline. For assuring the faultless memory status, we need some data protection mechanisms implemented in the system. So, if we start with one memory block, before we write data into the memory, we need to have a block for calculation of error correction codes. This is typically based on a data word that enters the system. When we read data from the memory, we are also reading the ECC code that was stored during the write cycle. Each information is sent to the ECC check and correction module. At the output, we are having a corrected read data and the ECC status check information. In some advanced system with stricter safety targets, we might have a situation that ECC calculation and check is including the address information together with data. From verification strategy perspective, we need to define a hooks in the system where we will check the ECC mechanisms are implemented according to the functional specification and safety requirements. Here the ECC agent is required. This agent needs to have the ECC model connected to the primary data source. Further, the ECC agent must check that the write cycle is correct. This write checker is taking reference information from the ECC model and is checking if the system behavior complies with specification. Next, the ECC agent also must investigate the read cycle. Here, two hooks are required in a system: the output from the memory and the output from the ECC check and correction module. The reference data is also taken from the ECC model. And finally, the ECC agent must report the ECC status information to the system controller. From the functional verification perspective, those are all passive components and functional checkers. But our ECC agent also needs to support the active error injection to the system, emulating the permanent or transient faults that might happen during system lifetime. For this, we need to have a constrained random pass functional model, which is generating required error types. Those errors can be of permanent type and are typically connected to the memory models. For verifying transient faults, we are interested in the data manipulation on the read data path. Further, the ECC agent must have the ECC predictor to see if the status reporting from the system is according to the expected behavior from the functional verification model perspective. With this short analysis, we can see the functional verification challenge in front of us and the verification of the functional safety mechanisms is concerned. Firstly, we need to have an error injection inside DUT. Since verification needs to have insight into DUT internal signals, a white box verification approach is required. Standardized black box methodology is not applicable for verification of the functional safety features. In this case, error reports are good things to see. We are expecting to see errors reported from the system. Usually, error reports are indication that something is not good. But here, we want to see error reported from the system and the verification environment. This means that the DUT functional state is disturbed and some actions are expected. With this, the classic verification tree is growing a new branch to meet ISO 26262 requirements with need for white box error generation and a new verification methodology. From the tools perspective, we are having usual flow, which is starting with formal verification methods, continues with functional verification on block level. Then, subsystem verification is concerned before the full IP or full chip verification is put in place. At the end, we are having software-based tests on an application level. And please notice that the DUT size is increased in this verification flow from the formal verification to the system level verification that includes software and full IP approach. On the other side, randomization levels are also different. Full randomization mode is applied to smaller RTLs and is decreased as we progress to the system level, where mostly directed tests are considered for covering specified scenarios. Please notice that this scheme is also having a V shape and is following the safety ISO 26262 V model. From the safety UEC architecture perspective, an ECC agent needs to have ECC modeling, ECC checkers, error injection, error monitoring and prediction, error reporting, and recovery flow implementation. From the verification perspective, those are all requirements are aligned with typical safety agent architecture with sequencer, BFM, signal sampling, collector, monitor with scoreboard and checkers block. The environment is also required to have specific configuration parameters and a register model. Note that for the error injection, we need to have a specified signal list where faults are randomly injected. Error injection constraints are defined with the sequence driver implementation, and actual signal upset events are defined with the safety UEC bus functional model. From the error injection perspective, we have two options, signal deposit or signal force. Whatever we choose, the error injection must be implemented by bit flipping on the design side. Signals which are corrupted from the verification environment must be agreed with design team. This is a crucial requirement for achieving required safety targets. But while defining this list, try to select registers and not wires or nets in a design. Note that Verilog nets are having a resolution function, which might have unexpected value if there are multiple drivers on that net. For example, if verification environment is driving this net with target to inject transient error, and design is also driving that net to different value in the same simulation time due to other functional requirements, we might get unexpected value on that net due to varied or resolution functions which will be applied by the simulator. To summarize, signal deposit gives a value to a net or register that will propagate forward. The signal retains that value until its next scheduled change. And signal deposit should be used for rejecting permanent faults or for corrupting memory bits. Signal force is slightly different mechanisms. It forces a value to continuous assignment that will propagate forward. It overrides all other drivers and stays in effect until replaced with another force or cancelled with release. This method should be used for injecting transient faults to the system, but together with signal release. Let us have a look on an example for transient fault injection. For example, we have a system Verilog task which is forcing a corrupted value to a signal at negative edge of the clock. Depending on generated error type, This task will force a value to a data signal or to a signal that holds parity bit information. If the system enables double error injection, the task may force a corrupted value to both data and parity signals. Then, verification environment must also have the task for releasing the force to model transient fault injection. This task must be executed after the error is injected. In this example, error injection is on negative clock edge, so signal release can be with next rising edge of the clock. In order to be sure that there are no race conditions with monitor or any other part of the simulated Verilog code, we might want to move the signal release slightly after the rising edge of the clock signal. And then, depending on the injected error type, we are releasing data, parity signal, or both. From the timing perspective, the error can be generated on negative clock edge. Force and release task can be started with the next rising edge of the clock. Then signal force is applied on the falling edge of the clock, and signal force is released slightly after the next rising edge of the clock. This implements error injection for a transient fault which was active slightly longer than the half period of a clock cycle. But this is enough since we have this active rising edge of the clock where system is expected to record this transient fault, and hopefully we will see with our verification environment that it's moved outside the stable state and that we will have the absent event identified by our verification environment. When a critical event is detected, a specification might request that all data processing is stopped and reset is executed. With UVM phases, this can be implemented straightforward in a verification environment with rerun of the reset phase. The simplified sequence could look like this, with the execution of the UVM phase jump method in the event of double error detection. When a phase jump occurs, all running phase tasks, their children and their local variables will be wiped clean. Also scrubbed away are any running sequences that were not launched during the main phase. Components such as scoreboards that retain some state in their fields will need to clear themselves when they enter the reset phase. Thanks to the universal verification methodology, this approach is independent to a verification language that is used in a project. Please notice that this verification methodology is developed with a verification environment based on Specman E with UVM. And here we are showing the same approach with System Verilog UVM verification approach. Another important aspect from the safety UVM implementation is the safety monitor. This block has to observe system behavior when there are errors being injected, but also in the cases when errors are not injected in the system to make sure that the false error reports are not detected with DOT. With this definition, the safety monitor must execute 3 threads in parallel: the signal sampling, idle monitoring during periods when errors are not injected by the verification environment, and error checking when transient faults are being injected from the safety UVC BFM. For example, we can start those 3 threads from the UVC monitor after the reset period is finished from the pre-main phase task. I've seen quite often that verification environments in many companies are taking UVM phases for granted, and they are not using the benefits which are offered with additional tasks. Please do not be afraid to use the different methods that are offered to you when you are using UVM-based verification environment. They are implemented for you to help you in achieving your verification goals. Another very important aspect of verification methodology for functional safety is to make sure that the error recovery flow works. It's great to see that if injected error is detected by the system and reported to a user through the specific mechanisms, such as interrupts, for example, and that then appropriate control action is taken. But to make sure system continues with normal function, is required to see if the error recovery mechanism is in place as well. For example, if error is reported from the functional safety monitoring block, user must check the error source with reading appropriate status register. Then, depending on the error source, certain action must be taken. After this action is completed, verification environment must make sure that normal functionality is continued. For realistic modeling, recovery flows should use front door access to the status information, for example through the APB or AXI register access methods. Those transactions take certain time in clock cycles, particularly if clock division is applied on an interface that is used for accessing the registers. During this period, verification environment might randomly choose to inject new error onto the system, and this scenario is putting a stress on a verification environment with at least 2 errors injected, but only 1 error recovery procedure taken. Due to this, verification team must assure that ECC agents are unifying multiple errors into one recovery flow with atomic approach to a ECC error recovery. Functional safety mechanisms are also very important for assuring a lifetime reliability for in-system testing. Such design for testing methodology is usually implemented with a built-in self-test circuitry. Such logic is used for 2 main cases: chip validation in a lab before it is integrated in the final product, or execution of a test sequences while IC is integrated in the system and is in active use. Please notice that one of the automotive requirements is to make sure safety operation is assured for more than 15 years. In the literature, we can find 2 categories for BIST techniques. Online BIST is executed by circuitries in normal functional operation mode, and offline BIST, which is executed during power on reset sequences at the engine startup, for example. This is often called latent testing, for example. The online BIST is a real challenge, since it is mixing the normal circuitry function and testing mode. Some kind of interleaving of those 2 completely different operation modes is required by the system, and this is a particular challenge from the application perspective. If you look at the data flow of our AI processor, we can see the input memory content is fully controllable by the host software. The system configuration is also configurable by the software, and the transformation function is known and well defined. This means that with predefined input data and selected hardware configuration, we can exactly predict output values from the system. With this knowledge, we can define certain signature into the data flow of our AI processor. And this signature can be, for example, a CRC code or any other hash function or checksum algorithm that is mapping a data set of our arbitrary size to a fixed size values. Please notice that the input data can be organized in such a way to send the same data stream to each parallelized processing unit. And with this, we can have the same signature at each processing output. So we can also compare if all outputs are the same, which is additional check that we can implement in this process. This signature is intended to help us to perform the safety check of our system. Our target is to check that if circuitry is in operational mode and there are no stacked faults in the processing pipeline. In order to check this, we can define certain signatures at the output of the data processing blocks. Here we have 2 of them: the main MAC-based processing block and the post-processing block. To check the signature value, intentional random errors must be injected by the hardware itself or from the verification environment. This can be anywhere in the pipeline, starting from the input memory, continue to the data distribution and data processing blocks. Error confirmation mechanism must be in place in order to verify that ECC logic is functional. And please do not forget that functional verification environment is having the scoreboard for checking the AI processor behavior in normal verification scenarios without error injection to the data flow. In usual functional verification tests, target is to see that scoreboard is not reporting any errors. But in functional safety verification test with error injection, we desperately need to see the scoreboard to report some errors in the system. This means that the error injection mechanism have disturbed the normal functional data flow, And this is good situation from the functional safety perspective. It would be very strange to see the system not complaining after error is injected somewhere in the data path. But please be aware that there are certain challenges when we are injecting errors into the data processing pipeline. Corruption of some data bits might not have influence on the results and signature checks. If we look at the simple limiter, which is reducing the 16-bit value to an 8-bit results, if the error is injected outside the output value, it will be ignored and it will not have any influence in the signature calculation. Also notice that due to multi-cycle paths and pipeline organization, it might take several clock cycles for the injected error to have an impact on results and signature. In such data path, it is much convenient to use signal deposit for error injection, but please be mindful about variable resolution function. If we look at the required procedures for functional safety verification, they are much stricter and more formalized to comply with ISO 26262 requirements. Verification process must be enforced. Safety procedures is stricter and more documented compared to usual functional verification approach. And to achieve this, different mindset is required. The safety procedure is main point, not document for internal use. During functional verification of safety mechanism, it is required to have continuous review process in place. Our methodology is defining a 5-step sign-off process that includes these safety review meetings. The first review is reserved for test plan review. Here participation of all teams is required, including verification team, design team, architecture team, and project management. Then we have functional coverage review, also with the same participants. Later in the implementation process, we have RTL code coverage and verification code review. Finally, we have sign-off review with all stakeholders involved again. This includes RTL code coverage review and special focus on toggle coverage for all external signals. And please see that those reviews are continuously distributed from the project initial phases to the project implementation phase to the project finalizing phase. All review meetings have to comply with certain meeting procedures. Those require meeting reports to have information when was the meeting and who took the participation. What conclusions are made on that review meeting and which action items are identified. There must be follow-up meeting organized to track the implementation of defined action items until all of them are implemented. In order to follow all those activities, we need to have some kind of status tracking information. And this is an example of the status tracking sheet with clear definition which safety feature is concerned, with brief description and a reference to the safety manual chapter. The design and verification owners are also defined with design and verification status for each of the features that we identified. And then we are having the feature review meetings for all 5 meetings. Upon completion of each review meeting, we are recording the meeting date and meeting report is kept in a separate place. And please notice that there are separate meetings for each feature review and for each feature we have in our status tracking sheet. Please note that in this process, the biggest challenge is to manage different mindsets required from the participants. Usually, design and verification engineers are not keen to invest their time in documentation and meeting reports. But here, this is a requirement defined through the safety procedure, and standardization needs and a different mindset is required from all stakeholders. With this, I would like to conclude presentation for today and thank you for your participation in this workshop. I truly hope that you have found some use for your functional safety projects. Thank you again, and I wish you a fruitful DVCon experience with a lot of new information and learning opportunities. Goodbye and stay safe.